All right, well, I'll get started here. I'll begin with a word of prayer as I get up here. Heavenly Father, we thank you for this day. I thank you for the student, and we just pray that the other student would have a good practice and be able to watch us in due time. Help us to glorify you in what we do, and help us just understand a little bit more about how contraction mappings come into play in analysis. Lord, in your name I pray. Amen. So what did you think of the did the proof that I gave in the previous video, that make sense to you? Like, yeah, the Monox-Fix. It's not. It's, to me, it's just like one of these things that's relatively easy to prove, and I'll try to convince you today a little bit more about just like how useful it is. So let me just get straight into it, and I'm going to start with the existence. Oh man. Trash. I actually did hit the trash can. For the record, Audric, I actually got it in that time. Jacob won't lie. He will testify. Let's see here, his existence and uniqueness theorem. And so I'll try to be relatively unsketchy about this one, and then what I'm hoping is this doesn't take me the whole class, and then I can sketch how we use the contraction mapping idea in other proofs. All right. So the basic issue here is, how do you solve dy dx equals to some function of x comma y of x? All right. And you're also given that y of x naught is equal to y naught. So this is, of course, a initial value problem, okay? So this is the initial value problem. We'll call it IVP, initial value problem. And if we integrate this, right, you can integrate this from, say, x naught to x dy. I'll change the variable to t because we're using x in a different sense there, right? F of t comma y of t dt, integrate that from x naught to x, and this gives us that y of x is equal to y sub naught plus the integral x naught to x f of t comma y of t dt. All right, and so what I just wrote is the integral. It's called an integral equation, of course, because it's an equation involving an integral. And so we can trade this differential equation for this corresponding integral equation, and you can see easily that they have the same solution sets, right? If you can find a y that solves this, it'll be a y that solves that. And also it has that y of x naught is equal to y naught, because when you put x equals to x naught here, this integral collapses to 0, and you're just left back with y of x naught. So this is a solution to the initial value problem. All right. So in that sense, this is a little bit better than the differential equation in that the initial value is baked into it. That's kind of neat. And then what's done is we trade this for an operator. So we think about t of y of x, all right, is equal to, well, guess what? Y naught of x. And technically speaking, see here, to be fussy, well, yowzers. I guess I don't. It's fine. It's a constant here. And, well, oh man, all of a sudden I had a moment of, yeah, that's just a constant. I should leave that as a constant. My bad. All right, so y naught plus the integral from x naught to x of f of y, comma, y of t. Oh, my bad. I'm a dummy. Stupid. T, comma, y of t dt. All right, so that is, we're defining this operator t here, okay? Right. Now, if using the same letter is like a problem, you can make this into a G, to see better, this is where the g is going, here and here. All right. So check this out. The integral equation is solved by a fixed point of t. If we have t of y equals to y, then that's the same as the integral equation, which I should have given a name like star or something. Does that make sense? So like this is t of y, so it's kind of dumb, but so we can view this integral equation as this operator, as this fixed point for this operator equation. And this is the trick, like recast the given problem as a fixed point problem for some operator. And then, if you can find a context in which that operator is a contraction, then you can apply Banach's fixed point theorem to derive the solution, the existence of the solution. And so this right here is, let's see here. All right, so the proof of Banach's fixed point theorem, right? What was it involving? It was the essentially the thing we defined was like yn, yn plus 1 was equal to, in the current notation, t of yn, right? Where t was a contraction in the appropriate context. And so in this context, setting up a sequence of functions like this is called the Picard iteration. So this defines the Picard iteration. So the PDF I sent you, which is Appendix 13 of Nagel, Saff, and Snyder, he actually works out the Picard iteration for a specific example, and I think it's good to take a minute to do that. So let's do that. Example 1. So I'll look at dy dx equal to 2y with y of 0 is 1. So that makes my t of y, right, equal to what? Equal to y0, which is 1, plus the integral from 0 to x of, well, here f is 2y, so right, 2y. It's 2y of t dt, right? Okay, great. So that defines, I mean, to be fussy, this is of x, okay? So what he says, so y0, to get the iteration started, y sub 0 is just the constant function 1. All right? And then we do the first iteration to find y1. Well, y1 is 1 plus the integral from 0 to x of, well, 2 dt. So that's 1 plus 2x. So that's y1. And then technically y1 of x, right? Okay, fine. So y2 is then 1 plus the integral from 0 to x of 1 plus 2t dt. And I'm bad about this. You notice that there's, you gotta watch me, I'll make this mistake in this example. See that 2? I can't forget about that 2. It's here, and it's also here. So don't forget about that. And so if you integrate that, we get 1 plus 2x plus, 2x squared. Yeah, 2x squared. And then if we do it again, right, we get 1 plus the integral from 0 to x of twice 1 plus 2t plus 2t squared, which is 1 plus 2x plus I guess 2x squared again, huh? Plus 4/3 x cubed. All right. Now that might not jump out at you as what is that? But let me show you something. If we do e to the 2x, right? By the way, you've had differential equations, so you know the solution to this is e to the 2x, right?
Oh, yeah, sorry. Yes.
I mean, I can convince you, like you're like,
Yes,
and like now that you're thinking about it and asking yourself the question, do I know the solution to this? You're like, oh, I knew that.
Yeah.
I mean, right, lambda equals r equals to 2 c1 e to the 2x.
Right, yeah.
Fit the initial condition. That is the solution.
Sorry, yeah.
So this is the solution just by like guessing, nothing else.
Right, yeah.
And check this out. Well, the power series, the Maclaurin expansion for this is what? 1 plus 2x plus 1/2 2x squared plus 1/3 factorial 2x cubed, right? And what do we got? So the Picard iteration is literally just generating the Maclaurin series, actually, of the solution. Now, on this, I don't know which edition of Nagel, Snaff, and Snyder I'm using. This may be like the 4th or the 5th edition, the appendix I'm looking at. I'm not sure, but I'll try to figure it out when I post the video. If I forget, I'm sorry. But one of the footnotes here is really interesting because this calculation predates Banach. So like he says this method can be traced back to Liouville, who used it in 1838 in his study of linear second order equations. It was also used by J. Cauchy in 1864, by Fuchs in 1870, and by Peano in 1888. But it was Picard whose name became associated with the method because of his work on successive approximations in 1890 and 1896. Banach's fixed point theorem was 1922. So by the time Banach came and formalized the theorem, I think there were already like a lot of different people who were kind of doing it, and he just generalized it and did it nicely, like the proof we saw in the last lecture for an arbitrary, normed linear space. Now, if you look at the proof that's in the thing I sent you, you'll notice that like the fixed point theorem there is given for functions of a real variable. And he doesn't even talk about contractions. Like he talks about the thing I'm going through right now. If you look at the fixed point theorem in the appendix, they don't talk about contractions to start with. They just assume that you can bound the derivative of the function that you're working on. And then, so like, you remember I used the derivative was bounded to prove that gave us a contraction for the Newton's method and the thing you're just watching. So like, but anyway, all right, let me go on. So that's the Picard iteration, and that's basically what frames the proof here. If you look at the analysis, which is given, oh man. All right, let me skip past this here a bit. All right, so here we go. So here's the uniqueness theorem that I'll try to talk about. Assume f and partial f partial y continuous on the rectangle a comma b cross c comma d. And you're fine. And then this contains the point x naught, y naught. All right. Then the initial value problem we stated over there, okay, dy dx equals to f of x comma y of x with y of x naught equals to y naught has a unique solution. On some interval. X naught minus h, x naught plus h, where h is positive. All right. Moreover, the solution is the limit of the Picard iteration. That I was just talking about. And here the t is defined as I defined it to start with today, yeah? All right, so this is the existence and uniqueness theorem that we sometimes state at the start of differential equations, right? If you think about it. And so, here we go. So the starting point of the proof is to take the open rectangle, right? And replace it with, so here's your point, x naught, y naught. And what his opening move is to replace it with put a closed rectangle around the given point. All right, so let's say like this for the sake of the picture. All right, and we're going to call so the open rectangle is assumed as R. The closed rectangle is R1. And let's see here, R1, I'll define it for you. R1 is going to be xy such that the distance from x naught to x is at most h1, and the distance from y to y naught is at most alpha 1. Such constants h and alpha 1 exist because we're looking at an open interval of reals, and so you can do that, right? And this is a subset of R. All right. So then what? He says, since R1 is closed and the partial f partial y is continuous, basically by the extreme value theorem, there exists m and L greater than 0 by continuity of f and partial f partial y, right? Such that we have the absolute value of f of xy is less than or equal to m, and the absolute value of partial f partial y is less than or equal to L. Right. Now, goodness, I can't remember what I did in the last video. I've read too much, and I've forgotten what I've read versus what I presented. Oh no, it's my bad. Did the last video, did I do something where I worked with a set of functions S?
If you did, it meant the last 4 minutes that I got to it.
Oh, okay. Was I using this the last 5 minutes? Was it this?
That was where I
yeah.
ended the class.
Yeah, no, it wasn't there. It wasn't there. That's just, yeah, I think if that's what I finished with, that was just,
Yeah, no, you didn't. I think you did.
okay, that's just the modified Newton's method. Yeah. Okay, so I did prove the fixed point theorem as it's stated in our textbook, right?
Yes.
In section 1.4. Let me refresh my memory as to how that is stated. Okay, it's for a closed subset of a Banach space, blah, 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 blah. Okay, yeah. All right. Okay, fine. All right, I am thinking about the appendix. So in the appendix, there is yet another proof of Banach's fixed point theorem, and in there they have a proof which is based on having a oh, come on, where'd you go? Their proof is based on having golly, where'd that thing go? So on page 842 of the appendix, when you have a chance to look at it, and that's probably not now, and that's okay. See, this is I'll let you look at it. This is the theorem I'm thinking of. It's a fixed point theorem for operators. So that's what's, the whole Picard proof here is based on this. We're trying to, you know what, I probably should just, you know what I should do? I should write that. So, I think I can safely write that up here. So, he's got S equal to y in the continuous functions on the closed interval from a to b, such that the norm of y minus y naught is less than or equal to alpha. Now that norm is exactly the function norm that we've been using. It's the max of the difference of the functions y and y naught for x between a and b. That's how we defined the norm on the continuous functions on like the closed interval, right? That was it. So it's our definition. That's fine, and then he looks at G as a mapping from S into S, such that, you know, the operator norm of G. Well, I guess this isn't the operator norm. My bad. I mean, this is just G of W is a function. G of Z is a function. So we're still taking the norm of a function. And anyway, it's a contraction, so that's less than or equal to some constant k times the norm of W minus Z. All right? And for all W and Z in S, I believe, right? So in other words, this is the theorem. Again, this is page 842 of the appendix. Chapter 13. I call it appendix, but it's really chapter 13 in Nagel, Saff, and Snyder. And he calls this the Banach fixed point theorem for operators. And so that condition I just wrote down makes G a contraction. All right. We're assuming here, of course, K is between 0 and 1. 0 less than or equal to K less than 1. Well, then this is all the preamble. These are the assumptions. Assume that there exists this S. Assume that there exists this operator G, which is a contraction. Right? These are all the presuppositions of the theorem. What does it get you? Well, what it gets you is then y equals to G of y has unique solution in S, and yn plus 1 equals to G of yn converges uniformly to that solution. Right. And he says for any choice of the starting function, why not in S? So he says you can, it doesn't matter what why not you pick. If you pick a why not in this set S, for which G is a contraction, you set up the iteration. That iteration will converge to the fixed point solution, which for our intents and purposes right now is the Picard iteration, and the fixed point solution will be a solution to the integral equation that we phrased at the start of class, and that will be a solution to the initial value problem that we all start differential equations with. Now, no one in their right mind proves this in differential equations for the obvious reason, right? But here it is. So what's at play here? Well, so he's trying to set the arena. The whole point of this at the moment is to figure out what S is. What is the appropriate set of functions on which the Picard operator can operate? That's what's happening right now in the proof. Okay, we're trying to work our way to that. And so continuity of F and partial F, partial Y have been used to bound that, all right? And he says that, he says, well, suppose G is continuous. All right, let me say here. Let me say it this way. If G, come on. If you have G continuous on I1 equal to x naught minus h1 comma x naught plus h1, where the absolute value of g of x minus y naught is less than or equal to alpha 1 for all x in I1, then for such G, we have T G of x equal to y naught plus the integral from x naught to x of f of t comma g of t dt, right? Is continuous, okay? So that's what one of the things he's saying is like, well, okay, so if you take a continuous function and you do this to it, it's still continuous. Now there's some theory being used there. I don't think I've quite developed in this course, but like composition of continuous functions with continuous functions is continuous, and if you integrate a continuous function like this with a variable bound, you get a continuous function. You know, that's not surprising. Integration usually adds to the continuity of things. It doesn't take away, as a general principle. Integrations tends to be smoothing, you know. Anyway, so then what? Well, I ran out of board. I'm going to shift over to here now. Yeah, it's a good thing we switched rooms today, because otherwise there's no hope for this one. I hope we can keep using this room. It's way better. I don't know if these boards are bigger or if they just feel like they're bigger. You know? I think sometimes the rooms that just have one board separated like that, they actually put, insult in addition to injury, like however you say that. Like, not only is there just one board on one side and the other side, they're like smaller boards. I need to take measurements. I feel like they're actually smaller boards. All right, so for G, All right, so hence for x minus x naught less than or equal to h1, I'm going to try to speed through this. The absolute value of t of g of x minus y naught, all right, that's equal to the integral, absolute value of the integral from x naught to x of f of t comma g of t dt, closed absolute value, which is less than or equal to the integral from x naught to x of the absolute value of f of t comma g of t, closed absolute value dt. That's a property of definite integrals, right? The absolute value of the integral is less than or equal to the integral of the absolute value. And then this is less than or equal to m times the absolute value of x minus x naught. Because the value of f is bounded by m in this context, and when we integrate dt, we just get, you know, x minus x naught. Well, anyway, I probably need to, in any event, this is true. I'm not, to be fussy, I think to go from here to here, I'm presupposing that x is greater than x naught when I write that, you know? Because if x and x naught were reversed, that would be negative. Okay, but I mean, you could go from here to here, and I think no one should really bat an eye. So let's just do that, in the interest of not writing possibly untrue things. Also, I just got a little bit more board space back. So haha. That's good. All right, so then what? Okay, so he says to keep t of g inside R1. And now they draw this picture, which we may or may not be successful in understanding, but we'll give it a go. So here's not even close, but actually I'm gonna reclaim this up here. We know the problem we're working on, so I'm gonna reclaim this corner up here for this picture. And picture something like this. So here in the center of the picture, you've got the point x naught, y naught. I'm gonna insert it's like a bow, like a fan here. Here, this line is y is equal to y naught plus m times x minus x naught. This one down here is y is equal to y naught minus m times x minus x naught. The point in the middle, again, is the point x naught, y naught. All right, what else can I tell you? Here's through the middle. This point right here would be x naught plus h1. This point over here would be x naught minus h1 in our setup. Up here, you've got y naught plus alpha 1. Down here, you've got y naught minus alpha 1. All right, so this is the R1 rectangle, right? Yeah, this is the R1 rectangle, what we're looking at right now, okay? And he says to keep t of g inside R1, we need, he says h less than h2. All right. Let's see here. So I have a picture something like this. And here's a hypothetical. Here's a hypothetical picture of t of g. And the claim is that we need h less than h2, which is needing to be the minimum of h1 and alpha 1 divided by m. And we also need, as we'll soon understand, h is less than 1 over L in order for T to be a contraction. So the whole name of the game right here is we're trying to come up with the h that's in the theorem, right? There exists some interval where h is greater than 0, right? So we're trying to construct this h on which the solution is known to exist, all right? So that's the whole starting point. We're trying to figure out how to get h from the data. See if we can understand this. So yeah, so I need, so you see this here, this is how far T of G is from Y naught, right? Well, this is not that exactly, but certainly, like the norm of T of G minus Y naught is by definition like max, right? Of this. So anyway, let me not blather. Okay, so what I'm trying to get at here, this would be a problem. This would be a problem, right? There you've got T of G more than maybe outside of R1. So he claims if you the minimum of H1, where's H1? So okay, so H1 so that's H1 is just to stay in R1. I mean, H1 is necessary. Again, we're going to make the criteria is soon going to be, you know, absolute value of x minus x naught less than h, right? That's the same as x is an element of this thing, right? Okay, so that's what we're thinking.
Less than or equal to 8.
Oh, equal to, yes, thank you. So to put H1 here is just to put us inside R1. Alpha 1 over MC. We know, okay, so we know that the T of G is stuck between these two lines, right? So where do those two lines, well, those cross here, right? Where is that? Yeah, we can look at this triangle here, right? So here's the change in y, here's the change in x, right? For that triangle. The change in x is what we're calling, well, I don't have a name for it yet, but that's what I'm interested in. We know that change in y over change in x is equal to what? It's m, right? And what's y? Alpha 1 is by definition, right? So you got alpha 1 over that change in x is equal to m. In other words, change in x is m over alpha 1. That's why we're putting alpha 1 over m here. Because that's simply just how far over you go with the line of slope m. That's all. Right? If this line has slope m, and you're looking at how far it goes over when it goes up alpha 1, the answer is alpha 1 over m. And because we are assuming that we're assuming that, you know, I see so many moving pieces. So we're constructed f of x, the f of x is less than or equal to m, right? But the g, the slope of g can't be more than m, which puts it under this line with slope m, basically. So anyway, let me stop talking. Bottom line is assuming this condition on H, we'll put the graph of G, basically basically that truncates the picture here like this, if I can muddle my picture a bit. It narrows the context basically to here, where the T of G can't get out of the box with the new box, the shrunk box. Because assuming that M is bounding F, right? And assuming that well, this right here shows that the slope of T of G, I think, is not more than M. That's what this means, among other things. This estimate right here says that the slope of T of G is not less than M. Because if you look at that, golly. All right, enough. So we have that. And the reason for putting the H less than 1 over L will be clear soon enough. So here we go. We're going to let H equal the minimum of H1, alpha 1 over M, and 1 over L. All right? And then we're also going to let S equal to G in continuous functions on the interval I, such that the norm of G minus Y naught is less than alpha. We could just say alpha 1. And I is equal to X naught minus H, X naught plus H. Okay. So finally, there it is. That's the set of functions on which we can prove that the Picard iteration serves as a contraction. For this set of functions, the Picard iteration is a contraction. And yeah. So I'll mix up all my papers if I'm not careful. So all I've done here is just write out by hand things in chapter 13 of Nagel's and Snyder. I'm following it very closely. Okay, so one of the things I should notice is that so if we look at the absolute value of T of G of X minus Y naught, that's less than or equal to MX minus X naught, yeah? So we did that before, up there. But now we can say more, that's less than or equal to MH, right? Which is by construction less than M alpha 1 over M, which is equal to alpha 1. All right. Hence, the norm of the function T of G minus Y naught is less than alpha 1. All right. And what does that mean? What's that say? G is an element of S implies what? T of G is also an element of S. So that's part of what we need. We need that the alleged contraction is a mapping from S into S. That's all that is. And because the definition of S was, in part that we're looking for functions that are less than alpha 1 distance from Y naught. All right. And so to prove t is a contraction, I will need to erase more. Golly. Oh man. Well, I think that picture has served its purpose. Well, let me, was it in there?
Yeah.
Okay.
I'll just say yeah.
All right. Oh man. All right, so yowzers. Golly. All right, so we want to prove t is a contraction. We'll let u and v be functions in S. All right. And recall that we have partial f, partial y less than or equal to L. Thus, by MBT, mean value theorem. Here we go. This marker's trash. I know I got a good black one in here somewhere. All right, so here we go. So the absolute value of t acting on u of x minus t acting on v of x is equal to the absolute value of the integral from x naught to x of, big parentheses here, f of t comma u of t minus f of t comma v of t. We haven't used the mean value theorem just yet, okay? Closed absolute value. So that is going to be equal to the absolute value of the integral from x naught to x of okay, fine, yes, partial f, partial y, evaluated at t comma z of t times the difference u of t minus v of t. And that's all integrated over dt, closed absolute value. This is the mean value theorem step right here. Let me explain what's going on. We're holding t fixed, right? And we're looking at a difference in y values. See that? So the mean value theorem says that partial f, partial y is equal to the average rate of change in the y holding t fixed, right? But so like the average rate of change in y holding the x equal to t fixed would be this divided by that. But we multiply it to the other side, we have this. And here the z of t has to be somewhere between u of t and v of t. And that holds not just for one time, but for every time. We're really applying the mean value theorem at each time. So it's an application of the mean value theorem infinitely many times, actually. One for each t between x naught and x, yeah? So it's sneaky. But there it is. Now we know then this is bounded by L. So we can do that. You know, I had a glorious black marker earlier today. Where did it gone to? Where's it gone to? Show yourself to me. Where did I put it? Man. What? How did I? Maybe it's this one. Maybe it's this one. All right, so that is less than or equal to L times the absolute value of the integral from x naught to x of the absolute value of u of t minus v of t dt, closed absolute value, which is less than or equal to L times the norm of u minus v over I times the absolute value of x minus x naught. Which then is less than or equal to LH, I'll do it down here, less than or equal to LH times the norm of u minus v with respect to the interval I but you notice that by construction over here, we had, see this? We had h is less than 1 over L, which means that LH is less than 1. So we can say that this is less than or equal to k times the norm of u minus v I, where k is equal to LH is less than 1. Therefore, it's a contraction. And so the Picard iteration defines a sequence which converges to the fixed point. And then there's a little bit more. You should still argue that, yeah, we still should argue uniqueness. And, well, the uniqueness is given to us by the fixed point theorem. So the fact it's contraction, that does that for us. I suppose there's still a little bit of something. There's one nuance here. What was it? This is the point in class where I get tired. Some reason. Well, that's just about it. I've lost my place. Man. I should have stapled these, you know. No, that's not it. That's not it. This is the Newton's method thing. Is it over here? It's over here, maybe. All right. So if you're keeping score, we're on page 845 of chapter 13. Let's see here. He says, okay, it now follows from Banach fixed point theorem that T has a unique fixed point in S, so the initial value has a unique solution. Moreover, the solution is the uniform limit of the sequence of successive approximations defined by the Picard iteration. To complete the proof, we need to resolve one subtle but important point. He says this, is that although we have shown the problem has a unique solution S, we have not shown that every solution on the interval from x naught minus h to x naught plus h must lie in S. And so then he gives an argument to prove that if you had any other solution on this interval, it must in fact be the solution that we already have found. So uniqueness of solution is, I suppose, a slightly different thing than uniqueness of the fixed point problem. I don't know. Well, anyway, but you can read the paragraph here on page 845 for the rest of the missing details. I'm hoping I still have a little bit of time. Do I have a little bit of time? Oof. I really have a little bit of time. How long have I been? Well, let's say I have 5 minutes. So, okay, so for future, I'm thinking about the book we're using right now. I don't know if it actually has the analysis of like matrices. And I'm wondering, are you interested in the analysis of matrices at all? Because I can...
worked once. I tried downloading this summer to look at
Mhm.
a matrix, but that was before I had neural forms and stuff like that from this book.
So yeah, I think it would be worth... I think it would be worth a class meeting for us to talk about.
I don't have any knowledge whether I should be knowing them or not.
Well, it's something that easily gets left out of the undergraduate discussion because it doesn't really quite have a home. I mean, do you at the end of your linear algebra course then say, okay, now let's do analysis on these things? Like, no, you don't do that. You're just trying to get people to learn what an eigenvector is if you're lucky, you know? So how do you talk about a sequence of matrices and things like this, yeah? So I think it would be good for me to diverge from the book for just a second and talk about that stuff. Once we develop some, and so I think tied with that, I should talk about like differentiation over norm spaces. I'm not sure, I think that's in this book eventually, but I'm tempted to just spend a day or two talking to you guys about those things just because, I mean, Audric has seen some of this stuff before, but let me just show you the like quick and dirty of it. So if you have a function, right, from say Rn to Rn, so, you know, a vector valued function of a vector variable, then long story short, you can write f of a plus h as approximately equal to f of a plus the Jacobian of f at a times h. All right?
So is this like generalized linearization?
Yes, this is the generalization of the linearization. Now here the Jacobian of f, if you're curious, is just the matrix formed by partial f partial x1, partial f partial x2, partial f partial xn, and these are partial derivatives of a vector. Okay, so that's an n by n matrix. Now I'm specializing to n just for the sake of our current discussion, but of course this also makes sense when the dimensions of the before and after are not matching. It still makes sense. So then you can ask the question, is this function invertible? Is f invertible? Right? And so have you ever thought about this in one variable? What's the problem of, how do you find, you know, if I want to find the inverse, you know, like I've got y equals f of x, I'm going to try to find the inverse function, right? For example, y equals, you know, e to the x plus 3. What do? Yeah, so basically we solve for x, right? So we take the natural log of y, we get x plus 3, and then that gives us that x is natural log of 3, natural log of y minus 3. There you go. F inverse of y is equal to natural log of y minus 3. So to find the formula for the inverse, you literally solve for x. That's all you do. The same is true for a multivariate function. So if you're trying to say, I've got y equals to big F of x, and you want to find, you know, these are vectors. I'll put a vector on it just so you can tell. You know, you're trying to solve that for an inverse function, what do?